All right, all right, all right. How are you, friend? Nice to see you again for another week of mucking around, hacking in Haskell. I wasn't too sure what I was going to work on this week, but this came out pretty recently, or at least was announced fairly recently. This is Spectacle, a very Spartan project so far, but that's okay. We're gonna check it out today. I learned a bit about it, get it to work. Let's see if we can write it. So Spectacle is supposedly a replacement for, or this is what it is, an embedded a language for writing formal specs. All right. It is released by Awake Security, and it sounds like they wanted a replacement for another model checker called TLA Plus. TLA Plus is another formal specification language that I have some experience with. TLA Plus stands for the temporal logic of actions, which is what they're referring to in the README there. The plus refers to all the other things that the toolbox has in TLA Plus, which includes not only like the language, it comes with a tool called a model checker to run your models and check them. And maybe in this stream, I can explain some of what all this stuff means if you're not familiar with it. So let me know, chat, if you want me to go into that and into that zone and discuss some stuff like that. It also, like, TLA has like several different languages you can write it in that I'll translate to TLA Plus. So for programmers who are not terribly familiar with, like, TLA's more mathematical notation, it has like a C-like language and a Pascal-like language called PlusCal. It has tools for generating pre-printed PDFs of your specs for documentation purposes and posterity, things like that. Even has a little proof system. I've never really used the proof system myself. I've used like Lean and stuff like that, but it's there. Might check it out someday. Because TLA is a pretty nice little language. So this tool, Spectacle, is a Haskell version of that. It's embeds all. Apparently, it's gonna be feature parity with that language and then something else. So in their blog post about it, Awake Security says that they're frustrated with TLA Plus. They needed to have something apparently that was just like not only as good as TLA Plus, like feature parity wise, but can do a little bit more. Otherwise, like, why bother writing something that's just the exact same thing as what you're using, just a different. As much as I like Haskell, yeah, like rewriting stuff in another language just because it's another language seems kind of. Oh, I don't want your cybersecurity stuff. Awake Security, sorry. So I'm not sure, this blog post doesn't really go into the like extra sauce that is going into this. So I'm really curious because like I love formal methods and formal specs. I really like Haskell. This is the kind of project that I've been like tempted to do for years, but I've never taken it on because I just felt like I never really had the time to do it because it's a pretty big project to do. And it's not the kind of thing I would get paid to do. So I wouldn't have a whole lot of free time during the day to do it either. So it's always been one of those things, be like, it'd be really cool to build formal methods tools and to do them in a functional language like Haskell and maybe improve on things. So I wonder what they improved on, basically, is what I'm getting at. So I really hope that it does make formal specs more accessible and drive its adoption. Okay, so it does end up reading a lot like, when I was reading this, it does look a lot like you would have structure a typical TLA plus type of spec. Some implementations can be verified by spectacle. So this is probably the secret sauce that they're talking about here. Some implementations can be verified by spectacle to satisfy their specification. Okay. So maybe a quick 5-minute overview of what all of this stuff is. Why would you write, what's a formal spec versus an informal spec? Why would you write these things? What's the point of them? What do they do? What are they for? All right. An informal specification. Let me just get the yield whiteboard out here. So an informal specification, pow, is something you're probably very used to writing and when you're working in software projects, right? An informal spec is usually one where you've written it in prose. The language is usually prose. Right. So you usually like write, I don't know, markdown doc, or maybe you just write things on a notepad or a whiteboard. You know, you draw some diagram, like here's my load balancer and my web servers and my database, that kind of thing, and they all connect like this, and da 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 da. Right. But the language is usually prose, like plain English or whatever language you speak is written in. And you just describe the system that you want, and hopefully it encompasses the requirements. How much rigor you put into your prose is, pretty useful. Depending on the project, you might put a lot of work into writing like a very broken down requirements document, which is a kind of spec. Or you might just like write a few quick notes. Depends on the scope of the project and what you're building, right? For example, if you're just building a shed in your backyard, you don't need to go down and find an engineer and get a license from the city and all this stuff. You can usually get away with drawing something on the back of a napkin, so to speak, and just do a little bit of math there about how much material you need and whatnot. Not a big deal. They're usually like validated. Now, how do you validate that your design is like has any errors in it, right? If you draw a bunch of stuff on a spec and you think really hard, that's good, a good thing to do. But how do you know for certain that your rate limiter, rate limits properly, or that your job queue with its parallel workers works for, say, 10 parallel workers on a single queue? How about 20? Does it always ensure that the jobs are processed once in order? All those things. How do you check those, right? How are they validated? In the terms of usually in an informal spec, you can question mark, but we tend to say validate it after the fact, after we write the implementation. We write tests, maybe acceptance tests. right? So these are like the tests that are written as close to the spec language, your pros, as possible in order to say like, okay, this is working as expected. I'll accept this, an acceptance test, um, that kind of thing. Usually after the fact. But a formal spec is a little bit different. What makes it different from an informal spec? Right? The language is not just prose. What makes it a formal spec is the language is formal. And it's usually, almost always, some form of mathematical language. These vary between model checkers, between tools. What we'll be looking at tonight with Spectacle is based on TLA Plus, which is a smattering of first order logic, and predicate logic, temporal logic. And this is useful because the language is formal. Now when we want to validate it, we can. It can be validated by a model checker. And a model checker is a computer program that takes the spec, and because it's written in a formal language, it knows what to do with it. And what does it do with it? Well, a model checker basically runs the spec and checks various properties that you've defined in your spec and things like this, which I'll get into in a moment what that means. But that's the high level idea, is that the model checker can check the model, and it can verify that you've found design errors. It can find design errors before you've already implemented the system, right? Which is pretty important. Some of the most expensive errors are not necessarily like bugs and things like that. You might call it like bugs. They're quite often design errors, like, oh, we got this totally wrong. Like finding out that your worker queue doesn't actually guarantee the things you thought it guaranteed when you set out to design it and build it is a hard mistake to back out of when you're late into the development of a project. So using a model checker, like writing a spec in these kind of languages is like usually like maybe like a few hundred lines at most for even a very sophisticated system with a lot of moving parts, and yet can find most design errors up front, and without writing code. That it's pretty powerful thing to have. And then, but there's one problem with formal specs, which I'm hoping Spectacle has got some neat ideas for. And that's called the specification gap. Which we'll get to in a second. So the specification, the reason why you want to write, I want to get to that in a second. The reason why you want to write a specification in the first place is a couple of good reasons. One, yeah, you want to verify your designs, and formal specs are a nice lightweight to try things out without having to write thousands of lines of code in order to see, does my multi-threaded queue do work once, or does my distributed system, whatever, lock properly, that kind of stuff. So that's good, right? The other thing it does is it serves as really good documentation and understanding. When you write these things down and you have a computer validate them and check them for you, it often comes back, a model checker would come back with a traceback or saying like, oh, I found a trace through your system It can go from here to 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 here. That violates this property you wanted to hold true. And that's important news, right? That says, okay, well, I got to fix something about this design and change it. And then once you've fixed all those things and you've written out these properties and it all checks, then the person you pass the spec onto might need a little training to read it because it's not a widely adopted tool, things like that. However, the language is small enough that I find most people can learn it in a couple of weeks. And when they read that spec, it's unambiguous what your system does. Right? It serves as good documentation. And Microsoft uses this internally. I've heard from some of their experience reports using TLA Plus, is that they run some fairly complicated services with some very, very high level of availability guarantees on the Cosmos DB team, things like that. And so they use these specs internally to train engineers on these projects, right? And then sort of like the meta thing is like it gives you a deeper understanding of the problem and the complexity of it. Because once you start writing things down, it kind of shows you quickly how sloppy your thinking is. Okay, so the specification gap, though. Let's talk about that. All right, so you've written your spec. A lot of frequent question I get from people is like, okay, that's great. I've got this spec. Well, I get two, but the main one is this. Like, do I have to specify the whole thing? Why don't I just write the code? Isn't that the specification for the program? Right? Or how do I verify that my implementation is the main one? That kind of follows from this. How do I verify that my implementation actually meets this or actually implements the spec? Right, so the implementation is like all the source code you write. So after you write your spec, you go and write the program, which the spec might be a couple hundred lines of code and describes a very complicated set of behaviors, but the code is tens of thousands, hundreds of thousands of lines of code that actually goes out and does the thing, automates the computers to do the stuff, right? And you want to know of that like 30,000 lines or 100,000 lines you wrote that it's actually implementing the spec you think it's implementing, right? And depending how far away your implementation is from your spec, like how much effort you put into maintaining the distance between the two, is called the specification gap. So typically, like TLA Plus is pretty high level. You define things in terms of like sets and sets and functions, like mathematical functions, not procedures, as in programming language functions, but like mathematical functions. And you have like this very formal language, right? And it's very high level. You can describe really complicated behaviors in a spec. And like I said, it's only a couple hundred lines, but it can specify things that are thousands of lines long. So how do you know that once you've written code that it's still implementing the spec? And that's called the spec gap. And the way often one of the things you can do is that the properties that you write in your spec is a good signpost for your tests. Right, so here it is. All right, so typically you'd write, turn your properties in your spec into tests. And that's usually a good way of doing it. But oftentimes it's not quite enough. You just have to think really hard about it and be careful. You need, like Microsoft uses a lot of tools they've built around CI to continuously run their specs and run their test suite that verify those specs and then kind of like bring the two together, which is takes a lot of effort to do that. TLA Plus doesn't include any of the tools to do that. So there's language, there's other formal spec tools that bring it closer to the program, that close this gap a bit. Tools like Liquid Haskell and other like embedded languages like Daphne and F star, things like that. And they try to bring the spec into the language itself, so-called deep spec. All right, and the idea with deep spec is that you want to close this gap here. You want the spec to live alongside the program and for the two to never get out of sync. All right, so the spec always implements the program. The program always implements the spec. When you update the spec, it validates the program that you're currently using, so you have to update the implementation, things like that. I'm kind of really hoping that's what Spectacle is going to do, but we'll see. We'll see. So this is an exciting project. I'm kind of interested in checking this out because this might be something we want to work on the stream a little bit and play around with a little more. This might be the tool. I don't want to chat with anybody. Website, jeez. Just reading your security blog. Okay. So I'm going to fork this to myself for experimentation purposes. Cool. Let's do it. Nope. How? There, that's the one. Oh, it got nix. It's all nixified. Let's try that. Okay, so that's going to be unpacking and probably building stuff for a bit. Let's look at some of the examples. So I think they said there were some examples in here. Test integration. Okay. Very Spartan documentation so far. Okay, some specifications. Cool. So these look like some of the typical specs from TLA Plus. So it's a pretty good sign. Simple clock, rate limit, the die-hard problem, bit clock. Cool, cool, cool. All right, so it looks like we got some types here. Action, initial, and variant. Some functions, always, default interaction, things like that. Spec. Okay, you have to import specification, fairness constraint. Some other stuff from this part. Cool, cool, cool. So this looks like a bit of type level-ness. The little tick here gives it away for me, if you haven't seen that before. I'm not sure what to call that. But it looks like we're dealing with like lifted data structures here, like type lifted stuff. It's kind of like a quasi-quote-ish type thing. I don't know. But if you do any sort of type level programming or seeing any sort of type level code where you're defining data structures at the type level or structures at the type level, like this list. It's a type level list. You usually have this little tick thing in front of it. So I think the idea here with this is that we're defining some variables for our spec. Like or that's the type of the variables of our spec. I guess is a way to think of it. Initial starting state of our bit clock. Cool. So that's what initial is for. Giving it takes two parameters, looks like type here, our bit clock and unit. Cool. So it looks like that just defines or sets the initial values that our spec is going to start off. The initial values are the variables or that are involved in our spec are going to start at or be initialized to. So when you're writing a formal spec, the other thing that kind of makes it pretty formal, it comes from formal mathematics. And the idea there is, you might say, like, isn't math pretty formal? But not always. Not as formal as you'd think. Formal mathematics is like not leaving anything out, crossing all your T's, dotting all your I's, not leaving anything for the reader, not assuming anything, spelling it all out, which is somewhat tedious when you're writing like mathematical proof. But when you have automation like this with computers, it's not so tedious. So it's worth doing because they're easier to verify reproducibly in a reproducible way because like computers have to check them. So yeah, when you write all these variables in your spec, you got to use them all and define what they are. And so when you're writing your initial state, you have to say like, this is all the variables and this is what they're all initialized to. Then you usually define a bunch of actions, which it looks like this is the next part of the spec here. So next, action bit clock bool. So I guess this is the action and initial looks like they take like this type level type that describes all the variables involved in the computation or in the spec. And it looks a little bit monadic, so it's returning like a bool. So action is going to be some kind of either a applicative functor or some kind of bool or monad, but probably a monad. Plain clock pulls out the value of the current value, I guess, of the clock. This must be the notation for setting values. If clock equals 0, then return 1, else return 0. So a bit clock only just has 1 bit to it. Right? So that makes sense. Just flip it. And then return true. That's our entire action, next action. So invariant, this is kind of nice. This invariant type here tells us that this is a formula that we want to hold true. It's invariant over all possible states of our model. That might take some explaining, so we'll do that in a second. But the idea here is that we're going to write some kind of Boolean valued expression, some formula. Just always return this set.member. So the clock is always in an element, the value of clock is always in a member of this set, 0 or 1. A pretty simple specification, right? Don't get me wrong. But it's just a bit clock, it's just an example, right? Just to show you. And then I guess we have check in IO, which kind of makes sense. So this is specification, I guess, is how you tie all of these parts together. So specification for bit clock. takes an initial action. So that's an initial that sets the initial state of our spec, our variables, okay? Next action is next. So like from our initial state, where can we go next? Right, like what can we do? In this case, we can only do one thing. We can just do next. Let's just flip the clocks bit. Has no termination formula. That must be what. So TLA plus has the ability to check for various termination conditions in a specification. You don't have to specify. Quite often I turn them off, but it can check for checks for things like deadlocks or race conditions. So it can check your program for those, or your spec for those for you. And fairness constraint. Weak fair. Cool. I find this is something that's not, at least syntax-wise and maybe like spec-wise, not so. It's great in TLA plus, but this looks a little bit like presented a little nicer. What this is, fairness constraints. So TLA plus and Spectacle, I assume, enable you to use. The reason why it has temporal logic is because you can check. This is going to actually, maybe I should get into explanations of things, but basically, you can check concurrent or parallel algorithms or programs and specify certain properties about those things, like certain things must eventually become true, or invariance, where things must always be true, which is a safety property. But those things where things must eventually become true are so-called liveness properties. They are the things that happen over time in your program. Like I get to this state, and then once I reach this state, I must eventually reach the next state. I can be in 10 intermediate states. I can be in 50 intermediate states. I can be in 1,000 intermediate states. But I must eventually reach this concluding state at some point in time, right? And a fairness constraint is a way to tell the model checker that we want, instead of just retrying the same brute forced steps to get to that end state, or continuously trying this one action, we can give something like weak fairness, where we say like, well, just try something that works. I think that's what weak fairness is. And that just means like, well, if I can't do this one, then we'll try this other one. We'll try this other action. We'll try to come back to this other one later when it's possible to take that action, right? So, and eventually we might be able to reach our end state. And if we can, then our spec is good. If we can't, then there's an error. Strong fairness isn't often used in specs. I find it's not quite as useful as weak fairness, but it's a way of telling the model checker, kind of like a scheduler, that you want to make sure that every action gets an equal amount of time, roughly, or each action gets to execute. I think that's the way strong fairness works. It's been a while. I'm a little rusty on this, so don't take my word for it. But the general idea is that these fairness constraints can sort of flip around the scheduler. And usually weak fairness is usually what you want in the most cases, I find. That's all I got on that. Yeah. Okay, and then this has its default in here. I don't know what that is yet. Cool. So this is taking a while to build. Oof. Cool. So yeah, why don't we got probably a few minutes before it's done compiling here. So specs, model checkers, how do they work? They take your spec, right? They have these variables. Let's just draw out bit clock, represent it graphically for you. Fine. So we have the only variable in our state is this clock variable, right? And initially, given by the initial formula here, right? Clock is going to start out as 0, right? its value is going to be 0. That's our initial state. Right, that's initial state right there. So when we first start, when the model checker first starts our program and initializes, that's going to be the first action. We take in our spec formula, and then from there, we can do the next actions. All right, that's the second part. So where can we go from this initial state? All right, we can only take the next action. It's the only one in this spec. It's not very interesting, right? So the next state for clock. All right, if we read that formula, that's true. So it's going to return 1. It's going to set clock, the next state of clock in the spec to be 1. All right, so we set the next state to 1. So when this action is, working on the world, we have access to the prior state here, right? And then we kind of define what the next value is of clock, what it's going to be, using, I guess, this notation here. And so we define what the next state is going to be based on the prior one, right? So we've taken next once. All right, we've taken next once, and now clock is 1. What can we do from now? From here, right? All we can do is one thing. We can just go next. All right, and then so on and so forth. Because it's such a simple spec. All right, and that's going to be 0, and so on and so forth. Okay. What if we had something slightly more interesting? All right. A pair of counters, say. All right, maybe we have a left bucket. Initially, it's going to be set to initialized to 0, and like a right bucket. And that's going to be initialized to 1. I don't know. I'm just making this up. Okay. Now, we have maybe 2 actions. We could like increment left. We could increment right, or we could decrement left, we could decrement right. Right. We'll say incr left will increment left by 1, leaving right untouched. We can increment right, which will increment right by 1, leaving left untouched. We can decrement left, and we can decr right. We'll have the opposite things, right? This is kind of a dumb, silly spec. It doesn't mean anything, just for demonstration purposes. Okay. So right off the bat, just given these actions here, and say these are part of our next, any one of these actions, we could do incr left, or incr right, or incr decr left, or decr right at any point in time, right, from the initial state. What are the next possible states? We could take incr left. We could take incr right. We could take decr left. We could take decr right. Maybe, if, depending on how we write our specification, we could also just do nothing and change neither of the variables for some reason. But if we do incr left, what do we get? We got 1, 1. All right, if we did incr right, we get 0, and we got 2. If we did decr left, we'd get -1, 1. If we did decr right, we'd get 0, 0, right? And you can keep building this tree, right? Incr, again, from here, you got all the different possible things, all the different possible states. And I can keep going and going and going. It just fans out. It can get huge. So a very simple program can have a really large state space to explore. What's useful about this, what's interesting about this, is when you use a model checker to check things like invariance in our spec here. And this bit clock spec, our invariant is that, the values of our clock are always 0 or 1. It doesn't ever get set to anything else. It's kind of a trivial spec. Similarly, I'm going to find something somewhat trivial for this one as well. Say that left must always be less than or equal to right. All right, so pretend our invariant. Let me write that out in a different color. Let's pretend our invariant is that left must always be less than or greater than right. And so if this is a safety property, we're saying that left must always be less than or equal to right in any given state. All right, let's just pretend for illustration purposes, right? Is this always true? Going to be always true in this spec? In every possible state. If we go here, already we can see it's violated. Is fine here actually, right? 1 is less than or equal to 1, right? Same with anchor right. 0 is less than 2. -1 is less than 1. 0 is less than or equal to 0. However, if we went from left to anchor left again, right, we would get 2, 1. Here, we would see that if we took this trace, right, our invariant would be violated, and we would get a trace back, and variant violated. Right, and then our tool, in TLA Plus at least, hopefully in Spectacle as well, once we get it to build and test out some of these specs and muck around with them, we can get tracebacks, right? Because now we have this tree of possible executions, and the model checker went from state to state, walking through the tree, checking our invariants at each step. And as soon as it encounters this invariance violation, it knows what steps it's taken, so it can give us the trace back. First I went anchor left, then I went anchor left again, and there you go. This isn't true about your spec. It's not possible to maintain this invariant given these actions and the way you've written the spec. So you got to change the spec in order to maintain this invariant somehow. All right, another example, one more example. So this one's harder to map out, but what if our invariant wasn't a safety property? What if we allow left to go less than right as long as it eventually comes back to that state that left is less than or equal to right, but temporarily for some amount of time it's allowed to be greater than right. Yeah. So we could write that formula somehow. I don't know if I want to write it out in like the full mathematical notation because I haven't explained any of the notation to you, but you could write out something that is like left eventually safe, whatever that means. Right, and that might be defined by your formula here. It says like eventually left must be less than or equal to right. And the model checker can check that too using the temporal logic operators. All right, so we can take any interleaving of these intermediate states, right, even with simulating multiple concurrent actors or potential interleavings of state, like concurrent potential timelines, I should say. Maybe that makes it more clear, of the different sequences of actions, right? So you might have worker 1 and W2, worker 2, say, in our little example program. And now this is like a parallel spec with multiple multiple concurrent processes running. And we want this state to eventually reach like a safety level where left is less than right. Right? And we might have a different timeline for W1 where It's like I took inker left, and then I took inker left again. All right, and W2 might have taken, I don't know, inker right, and then something else, blah, 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 blah. And our model checker can actually check that if W1 took inker left, W2 didn't get a chance to run yet, and then W2 gets to run inker right. Well, in the state where W2 gets a chance to run inker right, or gets to activate inker right, we already have an invariant violation, but that's okay, because left must eventually be safe. And so as long as the sequence of actions between the two end up such that once this state is like begun where left is greater than right, it eventually comes back to being safe again, then the spec's okay, right? And that's like a temporal property. But that's roughly how, a rough bad introduction perhaps, to how model checkers kind of work. Yeah, man, still building. This is giving me a time on this stream. I probably should have tried building it beforehand. So if we don't get to do this tonight, what can we do instead for a bit while we wait? We could work on admin problems. Why not? Did all this talking about TLA plus and model checking. But still building spectacle here. Yeah. So I'm like, ooh, Nix. Nix kind of feels, I don't know if the same way to you, but it feels a bit like Gen 2 sometimes. We like recompile the entire universe in order to get started. Good times. Anywho, let's try Advent. Do I have that here? Yeah. Oh, it looks like we're in the middle of day 13. Let's see what we got done there. July 2020, day 13. Part 2. Not implemented. Did we finish part 1? I don't remember. It's been a while. Oh, yeah, part 1. Okay. Cool. Did that actually work? I think it did. Ooh, a bus has a type hole in it. Ah, we were working on part 2. Okay, cool. And I don't think, oh, whoa, jeez, what were we doing here? Part 2 solution. tuple sections. Feel like this was kind of an incomplete solution here. Just plant those code hints. Okay. Advent of code. Where were we? 13. Oh, I'm not logged in. Hoo-hoo-hoo. There we are. Okay. Right. One go cold for anyone that can find the earliest timestamp, such that the first bus ID departs at that time, and each subsequent listed bus ID departs at that subsequent minute. That's right. So like that cascading thing. So the next bus departs 1 minute after T. Tour, there are no, why is there no? Oh, right, these matter. That's right. We figured out why the X's matter. Okay. So like this one's 1 minute after, that would be 2, but there's no bus there, so it doesn't matter. No bus there, so 3 doesn't matter. That would be 4 minutes after T. So the index in our input matters here. That's right. So this is probably the messiest solution I've worked on. Like I don't understand what's going on just by the code here. Okay, that's all right though. Sometimes it happens. So where are we? We are flattening the schedule, concatenating together all those schedules. From start. I don't know why we pick a start. Oh, maybe because we wanted to like start, because we know like from the input that's probably going to be pretty high. Maybe that was the idea. And we filter those. And zip it together. We zip together the indexes. Filter the non-X buses. So the buses that we don't care about. So then we should end up with a list here of buses and indices. Sure, add tuple sections. I don't think that matters here for some reason. I'm not actually using a tuple section at the moment. That would like that. So what's my hole doing? Hmm. Yeah, I don't want to use tuple sections. Or why not? I don't know. Whatever. For some reason, it's breaking the LSP using tuple sections. Like now it's not detecting my hole at all. I guess this, second. Oh, it's code action added a function that I didn't import. So thanks, but no thanks. There we go. That's better. So we need a function like this, and with a tuple of integer. I think that's the the index in the list, the input list. And then this tuple is the bus with the state. It's bus state. Since we flattened together all the schedules, let's see, bus schedule. What were we thinking there? Was that, what would this do? This would... concat map. So this, the idea here was that we would take all of bus 7's schedule, then all of bus 57's schedule, and just append it on the end, concatenate it on the end of bus 7's. Then that would result in what would that result in? That would result in like bus index, bus ID, time, oh, and state, bus state. And that would be like something like 0, bus ID say 7, time 0, and the states are arrived and something else. In transit and stopped. And this might be like 0 again, 7 again, time 1, transit. 0 again, 7 again, 2, stopped. All right, and then we might have like the timeline for bus 1. Say 14 at time 0. And so the question is, what was I thinking that we turn this into our output? How do we search this list for our results? Right. When we filter out the, well, we're actually filtering out the, we're filtering for non-X buses. We're keeping the non-X buses. Or filtering out the X buses. Yeah. So, I find it's kind of like a search problem, I guess. We got to look at bus ID 7 when it stopped. Right, is the goal. Oh, departs. Well, I guess that's the same thing as stop because it's used for the first one. I just called it stop for some reason. It should be departs. All right, that's fine. Sort of, but not really. However, so if I get this row here, then a very naive approach would be to then go and find a potential stop point for the next one for bus 14 that meets my requirements. And then for a bus, whatever that meets the requirements. And then if that doesn't work out, then we go to the next time and next top point in time where 7 is stopped and try those. Which means that we would be kind of like looking, well, we wouldn't have to look at every timeline in every other bus's timeline. We just have to look for the ones after this one, whatever it is. So we would be able to kind of like jump to like 14. If we find a stopped here, right, we can jump to bus 14's first stopped element after time 2. Could do that. What else could we do? Transform this into a map. 2 is the time. And the value is the bus is stopped there. Along with their, because we had to multiply their bus index or something, right? earliest such timestamp. So we only need to return time. Matching their positions in the list. Okay, so this might actually be an interesting avenue. Maybe. All right, so in this example, we'd have like the bus ID. The bus IDs. That's all we need, I think. Oh man, I'm so excited about Spectacle, but jeez. Jeez, it's still compiling. Ugh. I wonder if I should kill this off and just see if it has a non-nix way of doing this. Like stack? Cabal even? I don't care. Well, it's got Cabal. Yeah. And we have to like make sure we have the environment stalled if it needs any, has any weird dependencies, but what's the command for that? I don't really use Cabal that much. Build. Build. Sure, let's do that. Maybe we'll get to play with Spectacle. Go back to this problem for a second. Yeah, I think we just need the bus IDs. Right, if at time 2, 7 is stopped here. All right, that's it. At time 3, right, 14 could be stopped here. Maybe 57 is too, I don't know. At time 4, and who knows. And what this would mean is that we would need to know, we would need to map the list. How could we query this structure to get the answer we want, is what I'm thinking, right? So if we ask this structure for because what if 7 is here too? That might not be impossible. Data. Let's look at our input data. All right, it just gives you bus numbers. All right, the bus stops every 7 or every 13 or whatever. All right, we need to know the offsets because we need to know, yeah, we need the bus index in the input list because we need to know that, sorry, this is 1. Yeah, it's better. Because we need to know this bus 14 needs to be 1 minute off. Okay. So the question becomes then, you know, like say for the, there still isn't really an efficient way to query the structure for this either, right? Because if we want to say, okay, let's pick a time when 7 is departed. That won't be 3 in this example. that would be somewhere down here at 9. Right, 7 would appear again here. Well, if we did 7, that's at index 0, then we know that 1 has to contain, or 1 greater than whatever index that is, has to contain 14. Right, so that would be 3. 3 would have to contain 14. If it does, that's good. And then say the index for 57 is, say, 4. Sorry, 57, if I could type thing. At time, whatever. Doesn't really mattered, but the idea is that, okay, well then at index offset 4 from that index, so we're at 3, so at offset 7 is 54 in that set. If it is, then that's good. So on and so forth. And then, failing that, we would just try all of these keys in order. But then all of the queries to figure out, you know, to query the answer, like, does this fit the requirements? Or should just be 1. Or n. And the number of bus IDs we have to look up in our input. All right, and then the keys would be the times. So that could be pretty large. So we're looking like an m, potentially n by m worst case, I guess. It's not great. For small n by m, it wouldn't be so bad. Oh, spectacle compiled, yay! Another time bus problem. Let me actually write this down so the next time I try it, we have something. Let's put that in a different folder so we don't end up trying to compile it. Okay. Let's take that, put it in part 2. Okay, save that. Yeah, that's fine. Check that. It's not done yet, but we'll add day 13 part 2 solution here. Yeah, I'll just save that locally and just not merge it yet. Okay. Spectacle. Let's try it out. Let's close all this stuff. Get rid of all this day 13 stuff. Gone. Let's close down that stuff too. Yeah, no, I don't want to. Cool. So what targets do I get in Spectacle? How do I run one of these? Let's try it out. Cabal project? Spectacle to Cabal. A lot of extensions. Cool, cool. View patterns, one I haven't used very much. A lot of these are pretty, I would say kind of mostly bog standard these days. In a lot of projects, depending on your project, of course. Cool, those are the exposed modules. It's got a nice test suite. Cool. The test suite, I wonder if the integration test suite, if it just runs all of those. We have a benchmark target, it looks like. Huh. No, like, command line program to run specs yet. Well, let's try the integration tests. How do I don't know how to run those. How do I do that? Cabal. Tell me. Or if you know chat, tell me. Run test suites. Is there a way to specify which one? Because we got two. Oh, that's just help. Cabal help test. So that tests all. Okay, we can just give the name. Cabal test. Integration tests. How about just test them? Sweet, sweet, sweet. I'm just going to poke around here. Okay, well, pretty well structured export list. Operators define, dot equals enabled. Wonder what that is. Throw error, catch error. Logic language. So this will be pretty familiar to TLA plus users. This is the ASCII representation of the logical conjunction operator. Maybe it's a synonym, an operator synonym for conjunct or disjunction. That's and an or, complement, whatever the opposite of whatever some variable is. I guess that's the operator for implies, and if and only if. Sweet. The test suite has run. Excellent. Unit tests have run. That's it. Okay. So I'm kind of curious if that's it. Hmm. I guess maybe because, well, see, TLA plus has like all of these operators, of course, but it also has, I guess it has to, but it has its own like types, which it's technically an untyped language, so unlike Haskell, but you could define things like sets and functions, like, but not even like Haskell functions, but functions, um, mappings or things that have domains and ranges. Which I guess maybe you don't really need in Haskell. I'm just curious how we are gonna start writing our spec here, or running a spec. I guess the idea is that we would use this as a library, maybe. Hmm. Is it even on Hackage? Spectacle? It doesn't need to be, but no, it's not. Okay. So let's start one with stack. Let's call it spectacle test. Spectacle test. Okay. Now with stack, we should be able to put one of our dependencies as spectacle and just point it to the file system where we have the code checked out. So let's try that. Yeah, let's just do the exe, whatever, spectacle test, blah, blah, blah. Dependencies. If I could type right, would be spectacle. And if we try to build this, this will give us an error. Of course, because it's like, what spectacle is not even a stack thing. Okay. Go stack YAML. We can go extra dips. Now, I don't remember the syntax for specifying a file path. Hopefully it's not too far off from this. Might have to look up the documentation on that. Looks like it's working. Hey, cool. Yeah. You can just take a file path, looks like. So it'll be useful for, like, if Spectacle's still kind of under heavy development, you know, just being able to check out a new version of it or my own branch of it if I'm working on it, that kind of thing. I just want to, like, run one, test it out, see what it's like. spectacle. Maybe I just didn't spell tests right. Ah, well, it did run them that time, but just said pass. Which is all fine and dandy, but I want to mess around with my spec and see if like it fails and if it gives me a trace back or how this is going to work as a user. This TLA Plus gives you a, I guess, kind of janky IDE, but it works and it's an IDE. Right. I'm not a huge fan of it, but it's like just such a convenient way to start with TLA Plus. But again, Haskell tooling, working with that, pretty all right. So I assume we would have where we just set up some imports here. Was it language.spectacle, I think? Cool. Yeah. Specification.bit, like that. Yeah, import language.spectacle, language.spectacle.specification. Cool. Got some of those. Awesome. Why don't we just take this? Ka-tow, ka-tow, ka-tow. Let's put that back at Awake. Because they're the original authors, not me. Yeah, you don't expect the function block application because I don't have all the extensions enabled that this library uses. So let's look at their Cabal file again and steal all of those. Not Cabal.project, but Cabal. Spectacle Cabal. That's a lot. Let's get package YAML. I think it's default extensions. Let's see if I can macro this. Almost. Ooh-wee. And let's go back here. Let's just restart the workspace. Hopefully LSP can pick up on all of those. Yeah, I can't. Oh well, whatever. All right, let's try building this. Sucker. Right. Import qualified data.set. That, which probably needs containers, unordered containers. Unordered containers. think that's the one. I'm not sure. I don't remember. Just containers. Okay. Hmm. Word 8. Okay, that's from. I have to fix that import. Huh. Well, we actually need to use overloaded. Oh, I think we have overloaded labels in the package, don't we? I wonder why it's not defined here. Okay, let's just add that. Overloaded labels. Yeah, some imports we're missing here for to get the spec to work. Copy those as well. Okay, will you build now? Yep, almost, except our main. Now this uses some kind of IO action they call check here. So let's see, lib. We can just run check. LSP, don't even know what I'm building here. Okay, cool. Let's try running it. Maybe that's how you're supposed to do it. Spectacle test. Okay, cool. Look at that. Prints a nice little success. Model checker satisfied all properties with 2 distinct states. Maximum search depth of 2. Maximum search tree width of 0. So, look, obviously, with the fairness stuff, I guess it detects stuttering, so it only went to 2. Remember the graph I drew earlier, the states, where it was like our initial state, you know, it was like here, and then because we can only take next in this spec, right? Next, so on and so forth. We didn't actually have to like specify any terminating conditions. There's no termination formula. It just, I guess, well, this is TLA, and I guess this one does it too, which is nice. Is that, you know, if we keep seeing next, infinity, like that's just stuttering and it's never going to end. We know that because of the specs, so don't search everything. We only have to generate so much before we've exhausted all the logical or useful states. Otherwise, it would just keep going forever, right? It was doing it naively. Cool. So what if we mess up this spec and say like mess with other invariant? What does that look like? Oh, we didn't build though, so let's build. Okay, well, this is something, it looks like. So reports an error, always violated, and variant property is false for this step. So reading this, it looks like we can see the state is of clock 1 goes to clock 0. I don't know if that's useful. Like it should be reporting is like I went into the state with clock 1 and then this was violated. So maybe I'm just not reading this right. Maybe the arrow should be the other way. But it's something. I think if I was going to write specs with this as an actual tool, this would need some love, which is why I think we should do this on the stream. We should work on this. Maybe. Maybe we could build an IDE for it. Maybe we could just build slightly better tooling and just be editor agnostic. I don't know. But that's okay. So that's what an invariant violation looks like. Let's try one of the more complicated looking examples and mess with that one. The Dijkstra mutex. Oh yeah, beefy. Oh, GHCI check. What were they doing here? Interesting. So what I want to try in a more complicated, complex example because I want to see, like, this is fine, but I want to see, like, do we get tracebacks, you know, like, if this is a more complex spec, it could be tricky figuring out what went wrong with our spec or what's wrong with our design without tracebacks. And I really like that about TLA+. So if I'm looking at this from the perspective of a TLA+ user, and I'm like, hey, use Spectacle, you should try Spectacle. You know, that might be a hard sell if we don't have tracebacks. So let's try that. Why is this pasting the wrong thing? Windows, why? Man. I'm gonna copy. I'm gonna paste. There we go. Okay, cool. Still got check. It's just an IO action. Hopefully you got all the extensions needed to build this and try it out. Did I get all the imports this time? Or language extensions. Ooh. Okay, yes. Okay, we do need, this spec requires more stuff. So, okay, so it looks like to me that instead of providing us with a lot of the primitives you would use to write a spec, you might have to build some of them yourself. Or use like normal Haskell types and values. Interesting approach. For sure. Unordered containers. Just, yeah. Do that for the hash map stuff. Process. So this might actually be nicer if you're a Haskell programmer than if you're a TLA plus user. So this module is defined, looks like it's defining the state associated with each process that's going to be running. So like modeling a thread that might want to use our mutex using this algorithm. And normally in a TLA plus spec, you would define this using a function, essentially from that would map whose domain would be your process ID to whatever its state is, and you define the state as like, you know, another record, like another function, or like a set with some stuff in it or whatever. But this we can use normal like Haskell records. Interesting. Guess we'll see what this is for. Okay, we're going to need this a module like this as well. Yeah. It's process.hs. And go to lib, and we'll just import process. This import list is messy, and I'm just going to ignore that for now. So we're just messing around here. Process. Yeah, we'll see if that builds. Except for hashable, which we need to add. And of course, it's using more extensions that we haven't enabled yet. And we need to do that as well in process. Well, probably for several in process. And here we go. That was pretty fast too. Maximum search depth of 719 possible states. Cool. Okay, so this model, this checks. How can I tweak this and test it with, say, how many processes and stuff like that can I test it with? Muck processes. Interesting. Constants. Is that something that comes from this? That's something we defined here in our spec. Num processes and the process set. Interesting. This is kind of like a weird thing, I think, in the way TLA Plus is set up, is that there are these kind of constants, this idea of constants, are often set as like parameters to the model checker. So like if you have a particular variable that you want to be defined by the model checker, so you can check with a certain scope, like say 3 processes or 5 processes, you set that usually as a parameter of the model. And I wonder how that's defined here in this spec. Right, like it's just done here with this. I wonder if this model check thing uses it somehow. Let's try it with 10 processes. That ought to be a pretty large state space to check. Again, we're gonna have to rebuild it because we have to recompile it every time we want to tweak that. So I'm not a huge fan of that at the moment. So that's going to take a while to run because 10 process for just 2 processes, we generated a tree of possible states. That was 719 levels deep. So the bottom, very, very wide, very, very large. 10 processes is probably going to be a lot. I wonder if this is going to be faster than TLA Plus's model checker, or if it's still performance-wise going to be slower for now. It is pretty new after all. And that's fine. But I like making things go fast, so that'll be fun if that's something we decide to focus on the stream. Okay, that's taken too long, so let's try it with just 4. Twice as many. And then, yeah, I don't know. We'll mess around with it for a little bit longer. We're running low on time here on the stream. Oh, let's try that. Chugging away, even on 4. All right, so as you can tell, hopefully, maybe you can tell, but maybe you can't tell. But I don't know. Anyway, blah, words. Generating, like a model checking generates the entire state space of the whole thing. Like that entire tree, it'll generate every possible combination and of values for all those variables, right? For all those interleavings of actions, we have, say, parallel, you're checking concurrent number of workers and things like that. So every possible sequence of actions that could be taken by the system. And that can generate a really large state space, even from a small number of processes we're seeing here, just 4. Right? It's causing my computer here to be like, It's partly to do with something called satisfiability. Partly, at least in this case, because like generating that whole tree of potential spaces and then doing things like checking invariants on that tree requires a lot of work, right? Because if a safety property means every possible state. So if we're saying we're checking for 4, I want to know, is this going to work for 4 processes? And generally when you're working with formal specs, right, when we're checking something with like a Dijkstra mutex spec, so a specification for an interprocess mutex, mutual exclusion lock. We're checking with 4 processes, all trying to do every possible interleaving of all the possible actions in this spec. And generating a really, really huge state space. And this takes like a long time to check, right? Maybe as we work on, say, the performances here, this will get better, or like in TLA plus, it's pretty good. But it still can be pretty a model. So you don't usually want to check with large, like say 10 processes. You might only check with like 2, maybe 4, whatever you feel comfortable with. That's going to give you a good idea about the correctness of your specification. Does it meet your requirements? Because we can't check for every possible number of threads. We can't guarantee this test is correct and the possible number of processes. It's going to check for a specific number because otherwise we'd be waiting for the heat death of the universe for it to check all that stuff. This is a little bit different than taking the approach of using like a proof assistant to check this mutex and these properties. A proof assistant would be able to say that this property holds for anything. If you can translate your specification into that proof assistant's logic, it takes like a very different approach to specifications that way. Harder to do. Won't go wrong there. Won't be glib about it. But it's definitely a different approach, right? And you get higher guarantees of it. But usually the theory though here is that if it works for 4, it's probably going to work for your production environment where you might have 6 or 8. Right? It's very, very likely that it would. And it's Alloy, which is a different model checker, has a design philosophy that I think is kind of interesting too, is that the small model hypothesis, which is interesting for this discussion because that hypothesis says that number of steps to get to that state, that error state. So checking it for large models is useful if you have needs to, but the majority of problems you're going to find in your design or in your spec are going to be in small models. So this is like on 2 processes. It looks like 4 is too many. 2 is fast. What about 3? Yeah, so for one of the first things I'd want to change with this is making model parameters something we can read at runtime so that we can tweak them as we go and not have to recompile. Goodness, good gravy. Even for 3 processes, the spec is... And that's due to you're seeing exponential explosion here, right? Like 2 processes, 700 and some odd states. Oh, what could possibly... How many states could 3 processes bring into the picture, really? I don't know if we're going to have time to wait for this to see. So if you have needs where you need to run a big model, you know, you're going to need a pretty powerful computer and a fair bit of time. So it looks like this model checker is going to need like some performance tweaking and some looking into. The one in TLA Plus has been around for a long time, so it's very mature and it's pretty performant, generally pretty fast, and even has the ability to like distribute some of the work of model checking across multiple machines. So if you need to check a really large model to be super, super sure, you can run it basically on a cluster if you needed to. So this one, yeah, even 3 processes is too much. Let's set it back to 2. Well, that's neat. That's interesting. Spectacle. Look, interested to dig in more and start writing some of my own specs. Let's see, 2 is fast, but 3 is too many. Too many states, too much going on. And that might be, so one of the drawbacks to using like the entire ecosystem of Haskell data structures is that it could be like in writing your spec, you're just using inefficient Haskell things. Like maybe you just don't have enough strictness in your data types or whatever. And so that's affecting your model checking run. So that might be a little bit hard to optimize for, but we can look into it. We could definitely look into it. Well, that's all the time I got for this week. Next week, or maybe during the week, on, oh, is the Discord even on right now, the Discord link? Because you should totally join the Discord if you haven't. Make that visible there. There we go. So join the Discord. Follow me on Twitter. I'm Agent Ultra on Twitter. You can follow me on there, on GitHub, of course, at Agent Ultra. And I'm also on the FP Slack and the functional programming Zulip. You can Google those and find them, links to them to get the invites to join them. I'm Agent Ultra there as well. And on Twitter, I might announce what we're going to do next week as I play around with this a little bit more. And yeah, I'm stoked. This is going to be a fun project to work on. If you have any ideas for a project that we could use Replicant for, maybe we could do that as our next project, perhaps. I've been using Replicant a little bit for prototyping stuff on work things, but I also kind of wanted it to maybe flex a little bit with it and try a web application using Replicant and something like PostgREST or maybe even Hasura. I don't know if it would work with Hasura, but maybe like PostgREST and Replicant would be best buddies for building apps with those. So yeah, but I just don't have any ideas for projects right now for that kind of stuff. So I don't know. I have ideas for libraries, and of course, this I think is going to be a fun one to try out and to work on. So that's all I got for tonight. May your monads always be free. May your types always check. Try writing formal specs and learning more. There's a lot of great resources for learning TLA Plus or Alloy. And of course, maybe we'll do some more on this stream. But that'll be for another day. Take it easy.